Welcome students to the 6th video module. Today we are going to learn about uniform bending of a symmetrically loaded beam. In all previous modules we learned about non-uniform bending. What is the difference between uniform bending and non-uniform bending? We discussed that already. In non-uniform bending, the radius of neutral axis will be different at different points. That is why we used a differential equation for finding the radius. But in the case of uniform bending, the radius of neutral axis will be same at every point. That is the basic difference between uniform bending and non-uniform bending. So in this case, the radius of neutral axis will be same everywhere. Now, here we are discussing about a symmetrically loaded beam. You can see a symmetrically loaded beam in the figure. The beam which is the beam is held between or held on two knife edges at a distance L between them, and weight is hung on both sides at a distance P from the respective knife edges. The weight on each side is W. We know that the bending moment, what will be the bending moment? Bending moment is force times distance. Here the force is W and the distance is P. So the bending moment is W times P, force times distance. And because of this weight, we can see that from the normal position, the central portion of the beam is raised by a quantity delta, which is the deviation. Now, when you apply an external bending moment to this beam, there will be an internal bending moment set up inside the beam. That also we discussed in all the previous sections. So the internal bending moment is given by yi over r, where y is the Young's modulus of the material, I the moment of inertia, the geometrical moment of inertia, r is the radius of the beam, which is same everywhere. That is the only difference between all the previous modules you learned and this one. Now we can equate these two expressions, get yi over r equal to W times P. Now, in order to find this expression, or in order to replace the radius with some known terms, which are the known terms here? It is length of the beam between the knife edges. It is a known or a measurable quantity. So we have to replace this radius with this length L and this depression delta or the deviation delta. So for that, we are extrapolating the beam into the form of a circle. You can see that the beam AB is the length between the knife edges and delta is the deviation, and R is the radius of this particular circle. Now AD equal to BD equal to L over 2, half the length, and CD is the deviation delta. OC is radius R. So what is OD? OD is OC minus CD, that is R minus delta. Now in a triangle ODB, we can apply Pythagoras theorem using that OD square plus DB square equal to OB square. This is the triangle. Now OD is what? R minus delta. What is DB? That is L by 2. So R minus delta whole square plus L by 2 whole square equal to R square. Expanding this, R square minus 2 R delta plus delta square plus L square over 4 equal to R square. R square cancel, and delta is a very small quantity, therefore delta square can be neglected, so that also removed, And finally, we get the expression for R equal to L square over 8 delta. Okay, I hope you understood this derivation part. Now, you have to substitute this radius into the expression for bending moment. Then yi over, instead of R, I substituted L square over 8 delta equal to WP. Rearranging that, 8 delta yi over L square equal to WP. And therefore, delta equal to WP L square over 8 yi. What is W? The weight hung on both sides. P is the distance of the point of suspension of weight from the knife edge. L is the length of the beam between the knife edges. Y is the Young's modulus of the material, and I the geometrical moment of inertia. Now, if the beam is of a rectangular cross section, then the geometrical moment of inertia, we already know that is I is BD cube divided by 12. Substituting that, we get the expression for delta as delta equal to 3 WP L square divided by 2 B D cube Y. Thank you, students.